Hello and welcome to part 2 of using Piper to do relief valve, pipe sizing, pressure drops, however you want to describe it. So part 1, we created this model of our relief valve, which is here. So we had this contraction, expansion. So it's a 1.5 inch inlet down to my nozzle, which we're approximating or modeling as 22 millimeters diameter. And then we're expanding to this 3-inch pipework. So what we're going to do now is put on the discharge pipework, and that's going to be relatively simple. So I'm going to put an expansion in here. So let's put some pipework. Double click on here. This is my length. So diameter 3 inches, just picks it up from the expansion. Maybe I'm going to expand straight after the relief valve, so I can put that in there. And you can start to see why I've got this yellow box. We're going to start having lots of pipes and lots of expansions. So this is my relief valve discharge. I'm going to expand the straight afterwards. So I'm going to have that 0 length. I'm just going to go valve flange expansion. So let me go into here. Downstream is 3 inch, and then I'm going to go up to 4 inch. I then got my pipe work, so it's then going to pick up that's 4 inch. We'll give it some length. Let's not give it 40, that'll be a bit too long. Let's give it 4 meters. This final expansion here, this is the final expansion to atmosphere. So you can see it's 4 inch inlet. We need to expand to infinity, which in Pell terms is 10 meters. So we're going to put that in there. And of course, we wanted to put bends in there. We could drop a bend in, just like we've done with the other programs. But we put some pipe work on there. But the key bit is that final expansion to atmosphere. We put a little expansion in there. Let's just check our conditions. So again, we've still got an inlet pressure of 6.6 bar gauge. We're still going to atmosphere. So our ultimate this system back pressure is atmosphere. So that's all good. So relatively nice and simple. Let's press calculate. It's going to twirl away. Now, one of the key things you want to check, of course, is that flow rate's not changed too much. And I know we sized it in the last example. As we start building this model up, that flow rate might change a little bit because it's not just flow through a valve. We've now got pipe work around it, and really want to make sure that we're understanding the pressure losses and the back pressures at the flow rate that will go through the valve. So say in this case, we're doing rated capacity. So following an API 520 part 2 kind of approach. But we want to make sure we got that flow rate correct. So we'll keep looking at that, and maybe we might need to tweak it just a smidge because we want to make sure that flow rate is right. We wanted, let's just double check. So we go back 0.749, 0.746. I can live with that. It's near enough. And again, we can just double check what's happening now. So we've got our static pressures. We've still got our discontinuity, we're still choking in the valve. And then when you start thinking about what this back pressure might actually be. So that's our inlet to our valve, that's our expansion. So you can see that's got a big pressure loss across there. And that there is the pressure after the expansion. So that's the pressure, that's the way Piper works. It gives you the pressure just after the valve. So the pressure of that outlet flange is 0.037 pascals absolute. And then on this side of the expansion, it's 1.03566 pascals. Not easy to understand. Don't really understand pascals. So not pascals absolute. So I'm going to go into the options, and I'm going to say I want engineering units, and I like bar gauge rather than anything else. So I'm going to change that in this model. And then this makes a little bit more sense to me now. So actually, just at this outlet flange, it's just below atmospheric. And that's because things are expanding. We've got Bernoulli's going on. It's a flowing pressure. It's a static pressure. So we're actually just below atmospheric pressure. As we leave this second expansion, we've got a little bit of back pressure. And you sometimes get this in models. You'll see it in Adrian. if I get these, I tend to use this number as the back pressure, even though technically by the standards it's that. I think if you start putting it's -1%, we're going to start confusing people a little bit. And really what we just want to say is less than 10 typically. So I tend to, again, it's kind of a little bit worst case. I prefer that number. It makes a bit, yeah, it looks right. If you start putting negative pressure losses, people start to go, I'm not entirely sure what this means. So that's why I would put that on the spec sheet, but technically that's the correct one. But that's good. We've got a back pressure that's going to be less than 10%, 6-bar gauge, relief valve 0.6. Absolutely happy days on that one. We've got our expansion to atmosphere, so all is good. That's our back pressure. We just got the inlet pressure to go, and that's the easy one. See you in part 3.